So far, we have implemented only a single AXI master interface that is used to transfer data for all the three function arguments. When implementing the final design with SDXL, the software will automatically associate the master AXI port to one of the available DDR memory banks. Nevertheless, depending on the target platform, multiple DDR memory banks might be available, and SDXL allows to bind different AXI master interface to different memory banks. These effectively allow to make full usage of the available bandwidth to the DDR memory by reading and writing in parallel across multiple memory banks. In order to leverage multiple memory banks, first of all, we need to specify multiple AXI master ports. To do so, we can simply bundle the arguments using separate bundle names. In our example, we are targeting an alpha data, which features two memory banks. Hence, we can optimize memory transfer by using two distinct interfaces for reading the values of the input arguments A and B. Here we specify gmem0 for argument A and gmem1 for argument 1. Finally, argument res is still bound to gmem0. As previously discussed, the memcopy calls effectively creates loops that read all the data element in a row. In order to read in parallel both argument A and B, we can instruct Vivado HLS to merge the loop that gets created by the two memcopy. This is done by encapsulating the two memcopy call within a basic block using curly brackets and using the pragma HLS loop merge. The pragma tries to merge all the top-level loops encountered within the basic block in which the pragma is placed. By looking at the performance report of Vivado HLS, we can now notice that the two memcopy loops were collapsed into a single loop, taking the same amount of iterations. And if we look at the schedule, we can see that the read operation on gmem0 and gmem1 are actually performed in parallel. At this point, we have created a kernel with multiple AXI master interfaces, but in order to implement the full design, we still need to tell SDXL how to connect the interfaces with the different memory banks available on the platform. In order to do so, we can set the SP argument when running the link phase with the XOC6 Xilinx compiler. This concludes our journey on interface optimization. We first described the types of architecture targeted by SDXL and focus on the memory transfer operations involved in the workflow of an SDXL application. Then, we presented three different optimizations for the communication between the kernel and the onboard DDR memory, which are memory burst, maximization of AXI interface data width, and using multiple memory banks.